Hello, my friends. This is lections on number theory. First of all, we will learn theory of divisibility. In this lection, mainly we will deal with integers or whole numbers. By integers, we will assume natural numbers, 1, 2, 3, and so on. Also, by integers, we understand not only natural numbers, but also 0 and negative integers, -1, -2, -3, and so on. We will denote these integer numbers by italic letters, A, B, C, and so on. As we know, sum and difference of two integer numbers and also multiplication of two integer numbers are integers. But if we divide A by B, result may be not integer. If a ratio of two numbers, A divided by B, is another integer number, then we can write A is equal to BQ. And this representation means that A is divisible by B, or B divides A, or A is multiple of B. In this case, B is divisor of A, and we write it as B divides A. So this notation means B divides A. Result number one, or theorem number one, assume A is multiple of number m. By definition, this means A is equal to A1 times m. Also assume that m is multiple of number B. By definition, this means m is equal to m1 times B. Then, in this case, then A is multiple of B. A is multiple of B means A must be equal to B times some number Q. Let's show it. Proof is quite easy. Having these two equations, 1 and 2, let's rewrite it. A is equal to A1 times m, and m is equal to m1 times B. Inserting this m in this equation number 1, we will have A is equal to A1 m1 times B. And this integer number is our Q, and this is by definition means that A is multiple of number B. Result number 2, or theorem number 2, assume we have equality K plus L and so on plus N equal to P plus Q plus and so on S. And these numbers are integer numbers, as I said earlier. Assume that all terms except just one term is multiple of B. And assume that every term in this equality except term K is multiple of B. In this case, element K is also must be multiple of B. Let's prove it. We can write our equality as K is equal to P plus Q plus and so on S minus L minus and so on minus N. And since every term in our equality except K is multiple of B, we can write P, for example, as P1 times B. Q can be written as Q1 times B, and S can be written as S1 times B. Along the same way, L is equal to L1 times B, and N is equal to N1 times B. Obviously, in this case, K can be written as b times p1 plus s1, plus q1, and so on. It doesn't matter what we have here. It's important that these numbers are integer, and combination of these numbers, addition and subtraction of integer numbers, are integer. That's why this will be some integer number. Let's write it using classic mathematical notation. This means that q belongs to integer numbers. That's why k is multiple of b. Let's formulate our theorem once again. Let's repeat it. If we have this equality, and every term in this equality is multiple of b except one term, say this term is k, and each term in our equality is multiple of b. In this case, k is also a multiple of b. Next theorem is about representation of any integer number a as a equal to b times some integer number q plus r for any positive b. B is positive. And number r is less than b and not negative. And this representation is unique. Let's write here exist and unique. This denotion in mathematics means exist and unique representation. Let's prove this. Indeed, we can take multiple of number b, which is bq. We can take this number bq such that this is less than or equal than integer number a. We can always do it. And this distance between these two numbers will be r. And we can write a equal to b times q plus r, where our r is less than b and not negative. So this representation is quite obvious, but assume we have another representation. A is equal to b times q1 plus r1, where r1 is less than b and not negative. So we have two representations. And in this case, we can perform subtraction, and we will have b times q minus q1 plus r minus r1. And this is equal to 0. So we subtracted second equation from the first equation. And we have this. Of course, here, obviously, r minus r1, first is multiple of b. Why? Obviously, because of this representation and definition of being multiple. Next, obviously, absolute value of r minus r1 is less than b. This inequality is because r is between 0 and b, and r1 is also between 0 and b, and difference of r and r1, r minus r1, an absolute value of this number is less than b. And only case when number is multiple of b and absolute value of these two of this number is less than b is when r minus r1 is 0. So this is 0, this is 0, and we have b q minus q1 is equal to 0, which means that q also equal to q1. So we have q is equal to q1 and r is equal to r1. So our representation, this representation is unique, because these two numbers, q is equal to q1 and r is equal to r1. It was the proof of this theorem. So for any integer number a and some positive number b, number a can be represented as multiple of b plus a remainder, and this remainder r is less than b but positive. In this case, using this theorem, we can write, for example, assume our number b is 14. In this case, for number 177, we can write 40. This is equal to 14 times 2 plus 9, where our remainder 9 is less than 14 and positive, not negative. Number minus 64 can be, for B14, can be represented as 14 times minus 5 plus 6, where 6 is less than 14 and more or equal than 0. In our case, this is positive, but anyway, this inequality is also true. For number 154, we have 14 times 11 plus 0, and our remainder 0 is less than 14 and bigger or equal to 0. So this result is very important in number theory, and we will use it further.